In this video, we will examine the general 2D flow equations. In aquifers, it can be very useful to assume no vertical flow. That is, hydraulic head is allowed to vary with X and Y, but not with Z. Now, while we could utilize the 3D equations described in a previous video, it is often easier to examine flow through an aquifer if we design flow equations specifically to characterize 2D horizontal flow through an aquifer of some thickness. The formulation mimics the derivation of 1D flow that we've done before, beginning with conservation of mass and eventually substituting in Darcy's law. The main difference is that instead of stepping through this from the perspective of mass, we will actually consider volume. When we formulate the flow equations this way, we will be able to account for the thickness of the aquifer. Conserving volume instead of mass leads to a few changes to our original 3D equation shown here. One difference is that instead of describing the aquifer in terms of hydraulic conductivity, K, we are going to utilize transmissivity, T, which is just equal to conductivity multiplied by the thickness of the aquifer. So it's a way of taking conductivity into account in a volume, right? Because we're taking the thickness of the aquifer and just multiplying that by the hydraulic conductivity. And instead of using specific discharge Q, which is actually hidden in this general flow equation, there you can see it, specific discharge Q, we're actually going to use net specific discharge, which we denote with an N. So net specific discharge coming in the top and out the bottom of the volume under consideration. So the Q actually becomes N net specific discharge. For example, if you had 2 units of water come in the top and 1, that would be recharge in the top, and you lost 1 unit of water through leakage at the bottom, then you would have a net change of 1 unit of water, and that would be the net specific discharge. Using these relationships, the derivation follows as in the previous video, starting with conservation of mass of the water flowing into and out of the system, which is to say conservation of the volume of the water fluxing through the system, and then substituting in Darcy's law and making simplifications. When we do this, we arrive at the general flow equation in 2D. And for comparison, here is the 3D version from a previous video. You can see that we are using transmissivities, which take into account aquifer thickness rather than conductivities, which don't. In the 2D formulation, hydraulic head does not change in the Z direction. So this is 0 in the above equation. And instead, any changes to the volume of a column of water are accounted for with the net specific discharge here. Of course, this 2D equation simplifies further if transmissivity doesn't vary with space. In that case, you can pull it out of the differential and rewrite the equation like this, which of course could also be written like this. That's the same thing. We've just substituted in our Laplacian operator. Now, if there is no recharge or leakage, if n equals 0, then this reduces even further to this with no recharge or leakage, or if the flow is steady and this change in head is not going to be changing with time, then we would have. Now, of course, this means that if flow is both steady, if hydraulic head doesn't change with time, and there's no recharge or leakage, then del squared H equals 0, describing a system in which hydraulic head is steady. There is no variability in either space or time. So that's just a special case. And other special cases are outlined on page 233 of the textbook if you're interested. Both this video and the last considered the case of saturated flow. For completeness, this slide provides the generalized flow equation for unsaturated flow. That is, flow through a medium that is not yet saturated with water. In the case of unsaturated flow, changes in the water content, theta is water content, changes in water content occur and they must be taken into account. Both conductivity and theta, in the case of unsaturated flow, are actually dependent on pore water pressure, and so the unsaturated flow equations are also very commonly written in terms of pressure. Shown here. I know it looks messy, but hopefully you can still recognize this as a change in hydraulic head over space. The difference being that we've accounted for the water content of the saturated material and let that change with time as the substrate becomes more and more saturated. So these are the general flow equations for unsaturated flow. And these are the general flow equations for 2D saturated flow. This concludes the general flow equations 2D video. I hope it helped. See you next time.